The word law sounds confident, absolute, as if reality itself signed a binding contract and agreed to honor it forever. In physics, we use that same word with equal seriousness, but without any assumption of authority behind it. No one enforces a physical law, nothing monitors compliance, there are no penalties issued for violations, yet the law holds anyway. That fact alone deserves our full attention. There is no inherent requirement that the universe behave consistently. Nothing demands that identical conditions, repeated at different times or in different places, must produce identical outcomes. And yet they do, with reliability so profound that entire technologies, predictions, and measurements depend on it without the slightest hesitation. A physical law is not a command issued to nature. It is a regularity discovered through countless failed attempts to find exceptions. Drop an object, heat a metal, charge a capacitor, send light through glass. Change the location, the time, the observer, the surrounding conditions. The relationship repeats, not approximately, not most of the time. Exactly the same connection appears again and again and again. That repetition is the strange part. Physical laws do not explain why the universe behaves this way. They describe how reliably it behaves this way. Consider gravity. Objects accelerate downward at a predictable rate near Earth's surface. The law does not instruct the object to fall. It states that whenever mass and distance appear in that particular arrangement, the same outcome follows without exception. The law is a compressed summary of observed behavior written only after careful observation. Physics does not invent laws and impose them on reality. Physics notices that reality refuses to vary in certain specific ways. A law is what remains when preference, intention, and opinion are removed, leaving only what repeats, no matter who checks, no matter when, no matter where. A law is what remains when preference, intention, and opinion are removed, leaving only what repeats no matter who checks, no matter when, no matter where. This leads to a consequence of people frequently overlook. If something genuinely violates a physical law, it does not qualify as rare or unusual. It simply never appears in experiments, regardless of how carefully the conditions are arranged or how many times we try. That is why physical laws feel absolute. They are not supported by authority or decree. They are supported by every failed attempt to break them. At the same time, these laws are remarkably restrained. They do not specify everything that will happen. They limit what cannot happen, regardless of clever design or determined effort. That restraint is precisely where their strength originates. Taken seriously, laws stop resembling rigid formulas and start resembling the framework that holds everything else in place. And that leaves a question that refuses to disappear. If the universe follows laws so reliably, where do those laws come from? And why does nature obey descriptions written by creatures existing inside it? That tension sits at the very center of physics, and it does not resolve easily. The question persists partly because the word law quietly pushes our minds in the wrong direction. A physical law often sounds like a powerful rule running the universe from behind the scenes. Something active, something in charge. But at the deepest level, a law is none of those things. A law is a relationship. More precisely, it is a relationship that remains constant while everything around it changes. That is what separates a law from a mere coincidence. Materials can change, locations can shift, sizes can vary, conditions can transform, and yet the same connection between quantities keeps appearing. The law does not live inside the object being studied. It lives in how measurements stay linked across countless different situations. This already pushes against how people typically think about rules. Rules often sound like instructions. Do this. Avoid that. Physics does not operate that way. Objects do not consult a rule book before behaving. Nothing pauses to verify whether it is permitted to move. The law is never consulted in advance. The law is written afterwards, based on observation. What physicists actually track are numbers, distances, times, masses, charges, velocities. One value changes, another responds, and the search is for a link that refuses to disappear. When that link survives every conceivable attempt to disturb it, it earns the title of law. So a law is not something the universe follows. A law is something the universe never contradicts. That difference fundamentally changes how the entire subject works. It means laws do not push events forward. They exist above events, describing how behavior stays connected across many different cases. This is where everyday intuition tends to fail us. It feels natural to say a law causes behavior, gravity causes objects to fall, electrical laws cause current to flow, but the causal direction is actually reversed. Objects behave first, laws are written later to describe how that behavior remains connected across different experimental setups. The law describes consistency, not control. A simple example clarifies this. Take a spring, pull it slightly, it resists slightly. Pull it more, it resists more. Double the stretch, the resistance doubles. Change to a different spring, and the exact numbers change, but the link between stretch and force persists. The law is not hiding inside the spring, deciding how to respond. The law captures how two measurements stay linked over many trials at its foundation. That is all a law ever is. A stable connection between measurable quantities. Now comes a part that often surprises people. Laws do not describe events. They describe limits. A law draws boundaries around which relationships are permitted to exist. Inside those boundaries, many different outcomes remain possible. Outside them, nothing ever appears. No matter how carefully the setup is arranged, that explains why laws feel strict without being overly specific. They do not tell you what will happen next. They tell you what will never happen at all. This role becomes clearer when examining conservation laws. Energy provides one example, but the identical structure appears with momentum, electric charge, and angular momentum. These quantities move between objects, change form, spread out, yet the total remains fixed. Nothing in the system actively tries to keep the total unchanged. The conservation appears only when everything is measured and tallied. If an experiment ends with extra energy appearing from nowhere, the response is not excitement about a discovery. The response is certainty that an error occurred, because the law simply does not bend. This reveals another important feature. A law does not care about scale. The same relationships apply to falling stones, orbiting planets, vibrating atoms, and distant galaxies. The numbers change, the units change, the surroundings change. The relationship stays. That wide applicability is not assumed in advance. It is earned through rigorous testing in vastly different situations. This is another place where common expectations fail. People often expect rules to emerge from purpose or design. Physical laws come from neither. They are noticed because even disorder respects them. Chaotic systems obey laws just as strictly as orderly ones. Turbulent air motion follows the same equations as smooth laminar flow. A crashing wave respects conservation just as much as a precisely engineered clockwork machine. The law does not disappear when behavior looks messy. It remains firmly in place because it never depended on the tidy, predictable outcomes. This leads to an important clarification. A law does not guarantee prediction. It guarantees constraint. You may completely fail to predict what happens next while still knowing with certainty that specific outcomes will never appear. That certainty is where physics draws its fundamental strength. And this is where the word law truly earns its weight. A physical law represents the strongest claim that science makes. Stronger than a model, stronger than a narrative, stronger than an explanation. It says, across all tested cases, under all accessible conditions, this relationship holds without a single exception. That does not make laws untouchable or immune to refinement. New discoveries can refine them or reveal deeper structures lying beneath them. Even then, the older law survives intact within its tested range. Newton's laws still accurately guide the construction of bridges and predict the flight of baseballs. Ohm's law still governs electrical circuits. Thermodynamic laws still determine how engines and biological cells function. The law remains because it was never about achieving perfection. It was always about demonstrating consistency. At the deepest level, a law in physics is a statement about what remains fixed while everything else continuously rearranges. It is the frame that holds change together, making sense of transformation rather than being overwhelmed by it. And that brings back the question quietly waiting underneath all of this. If laws describe consistency rather than exert control, why does the universe demonstrate consistency at all? Why is there any regularity to discover? That question persists because laws do more than simply describe stability. They fundamentally shape how reasoning itself works within physics. When a physicist confronts a new situation, the first step is rarely making a prediction. The first step is elimination. A law immediately rules possibilities out. You may not know what will happen when two systems interact, but a law tells you definitively what outcomes cannot appear under any possible arrangement. That power comes from the fact that laws apply before specific details are filled in. They operate at the level of structure, not individual outcomes. This is how laws actually get used in practice. Suppose two objects collide. You may not initially know their final speeds. You may not know the precise direction they move afterward. But conservation laws have already fixed the range of the possibilities before any calculation begins. Energy and momentum place hard boundaries around every allowed result. Any proposed answer falling outside those boundaries is dismissed instantly. No matter how clever or elaborate the explanation sounds, the law does not predict a single unique future. It restricts the entire space of possible futures. This is why laws remain useful, even when exact prediction proves impossible. Weather cannot be forecast with perfect accuracy. Turbulence resists exact calculation. Human motion is wildly complex and unpredictable. Yet every one of these systems still obeys the same fundamental laws. Even when specific outcomes vary dramatically, the underlying relationships stay completely intact. This leads to a surprising and counterintuitive result. Uncertainty in outcomes does not weaken laws in the slightest. It actually highlights their proper role. A law remains exact even when predictions are rough or impossible. That feels backward initially. People naturally expect exact laws to produce exact answers. Physics demonstrates the opposite. Laws define constraints, so I am glad that even randomness and chaos cannot escape them. This becomes easiest to see in statistical mechanics. Consider a gas contained in a vessel. Individual molecules move utterly unpredictably. Collisions vary endlessly. Paths twist in impossibly complex ways. Yet pressure, temperature, and volume remain linked by precise, reliable relationships. The law does not track or follow single particles. It governs collective behavior without needing to monitor details. Nothing in the gas actively coordinates. Nothing deliberately averages. The law emerges because every individual motion still respects the same fundamental restrictions. Here, a law does not describe what each piece does individually. It describes what the whole cannot avoid doing collectively. This is one of the most counterintuitive features of physical laws. They actually grow stronger as systems grow more complex, more moving parts, more possible configurations. Yet the same constraints hold, without exception. That strength leads to consequences that frequently surprise people. One of them is this: multiple laws apply simultaneously. No system ever follows just one law in isolation. A falling object respects gravitational attraction, energy conservation, momentum conservation, and constraints imposed by material strength all at the same time. These laws do not compete with one another. They intersect. Each one trims the list of possible behaviors further. The final outcome sits at the precise intersection of all relevant constraints operating together. This is how physics maintains coherence across different domains. You do not choose which law applies to your situation. All relevant ones apply together automatically. The result is not negotiated or averaged. It is determined by strict compatibility with all constraints simultaneously. This explains why adding more information does not remove or override laws. It narrows possibilities within the space that laws have already defined. Another surprising result follows directly from this. A law can remain completely correct even when the explanation behind it changes dramatically. This happens repeatedly throughout the history of physics. Newton's laws describe motion with remarkable accuracy long before deeper theories existed to explain why they worked. Later developments revealed broader frameworks that fundamentally changed how motion was understood at deep levels. Yet Newton's laws remained valid within their tested range. They never stopped working correctly. They simply stopped being the deepest or most fundamental description available that tells us something profound about what laws actually are. They are not speculative guesses about hidden causes or ultimate mechanisms. They are careful records of verified consistency. That is precisely why laws age so well, while theories and explanations evolve. Now consider a paradox people frequently stumble into. If laws are descriptions written by humans based on observations, why do they feel so absolute and unbreakable? The answer lies in their origin and how they are established. A law is not declared or announced after a few successful tests. It survives relentless, sustained attempts to dismantle it. Physicists systematically try extreme conditions, unusual materials, edge cases, and clever tricks designed to find exceptions. The law earns its elevated status by refusing to fail under any circumstances. This gives laws a special epistemological role. They are not opinions that grow stronger through agreement or consensus. They are conclusions that grow stronger through active resistance to falsification. That resistance shapes their meaning. A law tells you something about the universe that remains true regardless of preference, perspective, or scale. It tells you that reality possesses structure that does not bend to narrative, desire, or interpretation. That realization carries weight far beyond equations and formulas. It tells you the universe is not arbitrary at its core. Events may appear chaotic, unpredictable, or bewilderingly complex on the surface, yet they unfold inside boundaries that never move, never negotiate, never make exceptions. That fundamental fact makes explanation possible at all. Without laws, there could still be events occurring. There could still be motion and activity. There could still be change and transformation. But there could be no science whatsoever, no comparison would hold across time. No experiment would reliably repeat, no lesson learned would carry forward into new situations. A law gives memory to the universe. It allows the present to resemble the past in specific, definable ways. And now the full meaning comes into clear view. A physical law says that beneath all variation, something crucial stays fixed. It says that while surface appearances change continuously, deeper relationships endure. It says that the universe does not reinvent itself moment to moment. That does not remove mystery from existence. It sharpens it. Laws answer how behavior stays linked while leaving the deeper question wide open. Why this structure exists at all. Physics does not claim to answer that ultimate question fully. It claims something narrower and far more solid. It claims that whatever the universe is fundamentally doing, it does so within limits that never waver. Those limits are what we call laws. They are not the actors in the story of nature. They are the grammar making the story intelligible. Without grammar, sounds still exist. With grammar, meaning appears in the same way. Events still happen in the absence of explanation. With laws, those events become comprehensible, comparable, and connected. And that is why laws sit at the absolute center of physics, not as commands, not as causes, not as decorative terminology, but as the unchanging framework that allows change to make sense at all. That realization tends to pull people forward because it suggests that learning physics is not fundamentally about collecting isolated facts. It is about learning the boundaries within which every fact must live. And those boundaries remain even as knowledge grows, even as explanations deepen, even as the universe continues doing what it has always done, behaving consistently, without asking permission, without requiring approval, without needing justification. At this point, the role of a law in physics comes into view without decoration or exaggeration. A law is not a belief about how the universe should behave based on philosophical preference. It is a meticulous record of how the universe has behaved every single time we have been capable of testing it, across different places, scales, and conditions. It is a statement of consistency that reality keeps confirming through experiment after experiment. That consistency is what allows physics to function as a coherent discipline at all. After a law is firmly established, it transforms into an indispensable tool. It allows reasoning without witnessing the outcome first. It allows confidence that certain specific results will never appear, even when the exact result remains temporarily unknown. That is the practical strength of a law in action. It does not describe the future in exhaustive detail. It limits the future to a narrow range of allowed outcomes, making the space of possibilities manageable. This explains why vastly different systems can be discussed and analyzed using identical laws. A swinging pendulum, a satellite orbit, and an electron bound in an atom behave very differently on the surface, yet they remain tied to the same fundamental constraints. Surface details vary dramatically. The underlying relationships remain constant. This also explains why laws survive scientific progress rather than being discarded. When physics advances into new territory, Earlier laws are not thrown away the way mistaken ideas are abandoned. They remain perfectly valid within the range where they were originally tested, even as broader, deeper descriptions add more structure underneath them. Bridges still stand because Newton's laws hold in their domain. Circuits still function because electrical laws hold. Engines still run because thermodynamic laws hold. That remarkable persistence tells us something crucial about what constitutes solid, reliable knowledge. Certain relationships hold without exception in every experiment performed so far. Energy does not appear from nothing. Momentum balances during every interaction. Electric charge remains conserved. These statements are not tentative guesses. They represent the strongest claims science makes about reality. At the same time, there are clear limits to what is currently known. Physics does not explain why the universe has laws. Rather than existing in complete disorder, it does not explain why these particular relationships exist instead of others. It does not explain why consistency exists at all rather than arbitrary chaos. Those questions remain genuinely open. That boundary between what is firmly established and what remains unanswered is part of the structure of scientific knowledge, not a weakness or failure. Laws tell us how far reasoning can proceed without speculation. They mark the edge where description ends and deeper explanation has not yet arrived. Taken together, this forms a clear and coherent worldview. The universe is not free of all constraint, and it is not fixed down to every microscopic detail. It operates within strict limits while allowing considerable variation inside those limits. Events can surprise us, outcomes can astonish us, yet they never violate the relationships holding everything together. That delicate balance explains why prediction can be genuinely difficult, while fundamental reliability remains absolute. It also explains why genuine progress in science comes from tightening constraints rather than adding elaborate stories. Each new law or deeper version of an existing one removes possibilities rather than increasing them. That narrowing represents real progress. The takeaway is simple and strong. A physical law is the strongest form of knowledge available about the natural world. It does not tell us everything about what will happen. It tells us with certainty what reality never does. That proves to be enough, because knowing what cannot happen allows technology to function reliably, explanations to hold across contexts, and learning to continue without collapse into confusion. The universe may remain incomplete to us. It may harbor mysteries we have not begun to fathom, but it is consistent. It behaves in ways that can be relied upon, and every time a law holds under testing, every time the same relationship appears in a new context, every time an exception fails to materialize, it confirms the same remarkable fact. The world is structured in a way that allows it to be studied, shared, understood, and explained again and again, without exception. That structure does not guarantee that understanding will be easy. It does not promise that every question has an accessible answer. It does not remove the hard work of investigation, but it makes investigation possible. It makes learning cumulative rather than circular. It makes knowledge transmissible rather than purely personal. And perhaps most importantly, it tells us that despite all complexity, despite all chaos, despite all unpredictability at the level of specific events, there is an underlying order that never breaks. Not because someone decided it should be that way, not because we prefer it that way, but because that is what the universe is, a place where certain relationships hold without exception, where consistency runs deeper than variation, where laws emerge not from authority but from reality's refusal to contradict itself. That is what a physical law represents. That is why laws matter, and that is why they sit at the foundation of all physics, not as the end of inquiry, but as the beginning, the reliable ground on which all further understanding can be built, tested, refined, and trusted